Okay, so at high level, here is what we are going to do. We are going to build an online store, like any shopping website you have used. And we are going to understand every important piece that makes it work. And we will do it in the exact order things actually happen. You open the site and we follow the request, one concept at a time, all the way down to the database and back. And my goal is simple. By the end of this, you should understand every core system design concept that comes up in the interviews. DNS, load balancers, caching, databases, queues, microservices, all of it. Not just what the word means, but how it actually works and why it exists. So, this is not a quick tour. We will properly teach each concept and then each time I will show you where it sits in our store. So, the whole thing stays connected in your head. And one thing to know upfront, this is a four-part series because there is genuinely a lot to cover, and I would rather teach it properly than rush it. This part 1 is about how a request travels the internet, how it even reaches a server. So let's start at the very beginning. You open your browser, you type the store address, and you press enter. The page loads. Simple, right? But how? What actually happened? Let's find out. So, the very first concept before anything else, DNS. And this one comes up in almost every interview. So, let's understand it properly. DNS stands for Domain Name System, and at high level, it is the phone book of the internet. Here is the problem it solves. You typed a name, let's say shop.com, but computers do not find each other by name. They find each other by a number called an IP address, something like 52.94.236.248. So, before your browser can talk to the store, that name has to become that number. That conversion, name to number, is the whole job of DNS. Now, how does it do it? Because this is the part interviews actually ask about. It is not one single lookup, it is a chain of them. When you press enter, your browser first checks its own memory. Have I looked up this name recently? If not, it asks a recursive resolver. This is a server, usually run by your internet provider, whose whole job is to go and find the answer for you. And if the resolver also does not have it, it walks down what we call the DNS hierarchy, which has three levels. First, it asks a root server who handles .com names. The root points it to a TLD server. TLD means top level domain. The .com, the .org part. The TLD server then points it to the authoritative name server. That is the server that actually holds the real IP address for shop.com. And that one finally returns the number. Now, that sounds like a lot of steps, right? And it would be slow if it happened every single time. So, here is the important part. Everyone along that chain caches the answer, meaning they store it for some time and reuse it. And how long they keep it is decided by a value called TTL, time to live. So, the second person who looks up shop.com does not repeat the whole walk. They get the answer instantly from a cache. That is why DNS feels instant, even though a full lookup touches several servers. Two more things worth knowing because interviews bring them up. One, the answer is not always the same IP. Big websites use something called GeoDNS, which returns a different server depending on where you are in the world. So, a user in India gets a server in India, and a user in the US gets one there. That is actually load balancing happening right at the DNS level. And two, DNS has different record types. An A record maps a name to an IPv4 address. A C name is an alias, one name pointing to another name. You will hear A record and C name in the interviews. Now you know what they are. So that is DNS end to end. And in our store, DNS is simply the step that took the address you typed and turned it into an actual server your browser needs to connect to. Now, your browser has the address, but it cannot just start sending your data across the open internet. It needs a proper, secure connection first, and that is our next concept. Okay, so your browser has the IP address. Now it has to open a connection to that server. And the way almost all web traffic does this is with a protocol called TCP. And a protocol at high level is just an agreed set of rules for how two computers talk to each other. TCP it stands for Transmission Control Protocol. So, what does TCP give us? One word, reliability. The internet underneath is not reliable. Packets of data can get lost, or arrive out of order, or arrive twice. TCP sits on top of that mess and gives you a clean, reliable, ordered stream. Every byte you send arrives exactly once in the right order. And it starts with something called the three-way handshake, and interviews love this. Before any real data is sent, the two sides say hello in three steps. Your browser sends a SYN, basically I want to talk. The server replies SYN ACK. Okay, I heard you and I want to talk as well. And your browser sends back an ACK. Great, let's go. Three messages and now the connection is open. And after that, TCP keeps track of everything. If a packet gets lost, it notices and sends it again. If packets arrive out of order, it puts them back in order. And quick contrast interviews like there is another protocol called UDP, which does none of this. No handshake, no resending, no ordering. It just sends the data and hopes it arrives. And that sounds worse, but it is actually faster. So it is used where speeds matter more than perfection, like video calls or live streaming or online games, where an old packet is useless anyway. Okay, so now we have a reliable connection, but there is still a big problem. Right now, everything traveling on this connection is in the open. Anyone in between on the same network or at your provider can read it. Your password, your card number, everything. So we need to encrypt it, meaning scramble it, so that only the two ends can read it, and anyone in the middle just sees nonsense. And that is the job of TLS, Transport Layer Security. And by the way, that is the entire difference between HTTP and HTTPS. HTTPS is just HTTP running inside TLS. The S is the security. Now, how does TLS actually make it secure? There are two ideas here and both come up in interviews. The first is encryption keys, and there are two kinds. Symmetric encryption uses one shared secret key to both scramble and unscramble the data. It is fast, but both sides need the same secret, and that raises the hard question: how do you agree on a secret over an open line where everyone in the middle is listening? And the clever answer is a method called Diffie-Hellman, which lets the two sides agree on a shared secret key without ever actually sending that key across the wire. This uses what is called asymmetric cryptography, meaning a pair of keys rather than one. So the flow is use this method once at the start to agree on a shared symmetric key and then switch to the fast symmetric key for the rest of the conversation. So you get both a safe way to set up the key and fast encryption after. And one nice property worth naming in an interview, because a fresh key is created each time and never sent across. Even someone who records the whole session cannot go back and decrypt it later. This is called forward secrecy. And there is a second problem TLS solves. How do you know the server is really the store and not an imposter pretending to be it? And the answer is a certificate. When you connect, the server shows a certificate that says, I am really shop.com, and it is signed by a trusted third party called a certificate authority, a CA. And your browser already trusts a list of these authorities. So if the certificate checks out, your browser knows it is really talking to the store. That is the little padlock you see in the address bar. So the certificate job is identity, and the Diffie-Hellman step job is the shared key, two separate jobs. And if an interviewer asks you to walk the TLS handshake at high level, it is just this: a browser says hello, the server sends its certificate, the two sides agree on the shared key, and then the encrypted conversation begins. That's it. So, putting it together, TCP gives us a reliable connection and TLS makes it private and verified. In our store, this is the step that happened silently the moment the page started loading. A secure pipe was built between your browser and the server, and now that pipe is ready. Your browser can finally send its actual request, and the language it uses to do that is our next concept. Okay, the secure connection is open. Now your browser sends its actual request and the language it speaks is HTTP, Hypertext Transfer Protocol. And HTTP is beautifully simple. It is a request and a response. Your browser sends a request, give me this product page, and the server sends back a response, the data. That is the whole model. Now, let's look at what is inside a request because interviews ask this. A request has a few parts. It has a method which says what you want to do. It has a path which says what you want, like slash product slash 42. It has headers which are extra information about the request, like who you are, what format you want back, and sometimes a body, the actual data you are sending. For example, when you submit a form, the methods are worth memorizing. Get means read something, just fetch it. Post means create something new, like placing an order. Put means update something. And delete means remove something. Read, create, update, delete. And the response comes back with a status code, a three digit number that tells you what happened. And these are grouped into families, which is the useful part. Anything in the 200s means success. 200 okay, it worked. The 300s mean redirection. Go look over there instead. The 400s mean you made a mistake. Like 404 not found, the page does not exist, or 403 forbidden, you are not allowed. And the 500s mean the server made a mistake, like 500 internal server error, something broke on their side. So 400s are your fault, 500s are their fault. That single line is worth a lot in an interview. And one more property, which will matter a lot later. HTTP is stateless. That means each request stands completely on its own. The server does not automatically remember your previous request. Every time you ask for something, it is like the server is meeting you for the first time. Now, that raises an obvious question. If the server does not remember you, then how does it know you are logged in across many pages? Hold that question. We have a whole concept for it later. For now, just remember, plain HTTP has no memory. And finally, you will hear two more words a lot: API and REST. An API, application programming interface, is just the interface one program uses to talk to another. It is the set of requests our server agrees to accept, and REST is the most common style of designing that API in a clean, predictable way. You have resources like products or orders, and you use those standard methods on them. So, get slash products reads the list, post slash orders creates an order. Two practical things interviews ask about a real API: pagination, meaning when a list is huge, you return it in small pages instead of all at once, and versioning, so you can change the API later without breaking apps that already use the old one. And you will hear a lot of alternatives to REST like GraphQL and gRPC. Just know they exist as other ways to build an API. And one last thing, HTTP is request and response, one round trip. For things that need to be live, like a chat or live notifications, you use a different kind of tool called a WebSocket, which keeps the connection open both ways. So the server can push updates to you. Just know that it exists. So, HTTP is how your browser and the server actually talk. In our store, this is the request that page went out asking for the product page. Now, that request has arrived at the server. So, what is a server and what does it do with your request? That is next. Okay, the request arrived at the server, but let's be precise about what that even means because client and server are the two most basic words in all of this. A client is the thing that asks your browser, your phone app. A server is a program running on a computer somewhere whose job is to answer those requests. That's it. Client asks, server answers, and one machine can serve millions of clients. Now, inside the server is usually not one thing, it is two, and the interviews sometimes check this. There is a web server, software like Nginx, and its job is to receive the raw request, handle the connection, and serve simple files quickly. And behind it, there is an application server, which is where your actual code runs, your business logic. So, when the request comes in for place an order, the web server receives it and passes it to the application server, which runs the real logic. Check the item, calculate the price, save the order. So, what does the application server actually do with a request? At high level, a few steps every time. It reads the request and figures out what you want. It may check who you are. It runs the logic. Very often, it needs data. So, it talks to a database, which is our next big concept. And then it builds a response and sends it back. And one small piece you will hear about sitting right at the front, a reverse proxy. Think of it as a receptionist for your servers. Every request hits it first, and it can handle the secure connection and decide which server to forward the request to. We will come back to it properly when we scale up. So the server received your request and now it needs the actual product data, the price, the stock, the description, and that data lives in a database. And that how data is stored and how we make it fast is exactly what the next part is about. So that wraps up part 1. We have followed a single request all the way from your browser through DNS, a secure connection, and HTTP to the server. In part 2, we open up the database and everything that makes data fast. If this was useful, subscribe and I will see you there. Welcome back. This is part 2. In part 1, we followed a single request from your browser through DNS, a secure connection, and HTTP, all the way to the server. Now, that server needs data. So, in this part, we cover where the data lives and how we make it fast: databases, then indexing, caching, and CDNs. Let's start with the database itself. Okay, the server needs data, the product's price, how many are in stock, your past orders. Now, you might think just keep it in a file. But a file stops working the moment you have many users reading and writing at once. And huge amounts of data you need to search quickly. Under requirement that you never lose anything. So instead, we use a database, which is at high level a specialized program built to store data safely and give it back quickly, even with thousands of people using it at the same time. The most classic type is the relational database. This is your MySQL, your PostgreSQL, and the SQL databases. And the idea is simple and powerful. You store data in tables like a spreadsheet. So you have a users table, a products table, an orders table. Each table has rows, one per user, say, and columns like name and email. And here is the relational part. Tables can be linked. An order row can point to the user who placed it. So you can ask, give me all the orders for this user, and it connects them. And the language you use to ask these questions is SQL, structured query language. Now, the single most important thing about a relational database and a concept that underpins a lot of what follows is that it gives you ACID guarantees. ACID is four letters and each one is a promise. A is atomicity. A group of changes is all or nothing. Either every step happens or none does. C is consistency. The database never lets its own rules be broken, like stock going below zero. I is isolation. When many people are making changes at the same time, they do not corrupt each other. Each transaction behaves as if it were alone. And D is durability. Once the database says saved, it is truly saved, even if the power goes out 1 second later. And those last two have real missions behind them. For isolation, imagine two people buying the last item at the same instant. Without isolation, both read stock 1, both sell it, and you have sold something you do not have. So, the database makes one of them wait, usually by locking that row, until the first one finishes. And for durability, before the database says saved, it first writes a change into an append only log on disk. So, if the power goes off, it reads that log when it comes back and replays anything that was not fully written. And the tool that gives you all of this is a transaction, a bundle of changes that the database treats as one single all or nothing unit. Let's make it concrete. When you check out, three things must happen together inside your own database. Create the order row, reduce the stock by one, and write a payment attempt record. A transaction guarantees you can never end up with, say, the stock reduced but the order didn't get created. Either all three commit together or the whole thing rolls back as if nothing happened. And one important detail, notice that charging the card is not in that list. The actual charge goes to an outside company like Stripe over the network, and you cannot roll back an outside company. So you never put that call inside your transaction. You commit your rows first, then call the payment provider, and you send a unique idempotency key so that a retry never charges twice. Later, a reconciliation job compares your payment attempt rows against theirs and fixes anything that disagrees. That is why anything involving money almost always lives in a relational database. So, the relational database is where our store keeps its truth, the real products, the real orders, the real stock safely. But relational is not the only kind of database, and which kind you pick is the one of the most common interview questions there is. So, let's talk about SQL versus NoSQL. Okay, so we have the relational SQL database, but you will constantly hear about NoSQL databases as well. And SQL or NoSQL is one of the most asked interview questions. So let's be clear about it. And the honest answer is it's not a trade off, not one being newer or better. The SQL database, as we saw, gives you tables, relationships, and strong asset guarantees. It is brilliant when your data is structured and connected, and correctness really matters. Its cost is that it's stricter and traditionally harder to spread across many machines. NoSQL is really an umbrella for several kinds of databases that each relax some of these rules to get something else, usually more flexibility or more scale. And there are four families worth knowing. 1. Key value stores like Redis or DynamoDB. You store a value under a key and you look it up by that key extremely fast, great for caching sessions. 2. Document databases like MongoDB. You store flexible documents, basically JSON, which is just a simple readable way of writing structured data as text with no fixed columns. Good when your data shape changes a lot. 3. Wide column stores like Cassandra, built to handle massive amounts of writes across many machines. And 4. Graph databases like Neo4j, built for data that is all about relationships like a social network. And many NoSQL databases follow a model called BASE that stands for basically available, soft state, eventually consistent instead of ACID. The key idea to remember is that last part, eventual consistency, meaning if you write something and then immediately read it from another copy, you might get a slightly old answer for a short moment until the copies catch up. That sounds bad, but for a lot of things, like a like count, a view count, it is completely fine. And in return, you get huge scale. So the trade is SQL gives you strong consistency and relationships. NoSQL often trades a little of that away for scale and flexibility. So, how do you pick in an interview? Simple rule. Use a SQL database when your data is structured, has clear relationships, and needs strong correctness. Anything with money, orders, users. Use a NoSQL database when you need massive scale, or a flexible shape, or one specific extremely fast access pattern. And honestly, real systems use both. And two quick related pieces because a real store needs them. The product images do not go in the database at all. Big files go in object storage, like Amazon S3, which is a service built just for storing files cheaply. And search, when you type words in that search box, usually goes to a separate search engine like Elasticsearch, which is built to find and rank text. A normal database can do basic text search. Postgres and MySQL both have full text features, but a search engine is built for ranking, typo tolerance, and doing it at scale. It is worth being able to separate those two out rather than saying the database for everything. So, in our store, the orders and users sit in SQL database. The sessions might sit in a key value store. The images sit in object storage and search sits in a search engine. Now, even with the right database, one problem remains. As data grows, finding a single row can get slow. And the fix for that is a concept called indexing. That is next. Okay, so let's say our store's user table has 10 million users, right? And you want to log in. So the database needs to find the one row where the email matches yours. The naive way, check every single row one by one until it finds a match. With 10 million rows, that is painfully slow. And this is exactly the problem that indexing solves. Another very common interview topic. An index is a separate data structure that the database keeps on the side, which lets it jump straight to the row you want without scanning everything. The simplest way to picture it is exactly like the index at the back of a textbook. Instead of reading every page to find one topic, you look it up in the index and it tells you the exact page. A database index does the same thing for your rows. And how it works. At high level, the index keeps the values in a structure called a B tree. And a B tree is a short wide tree. The top node holds the few values that split the whole range into parts, let's say up to M and after M. And each part points down to a node one level below, which splits again. And the bottom level holds the actual values, each with a pointer to where that row physically sits on the disk. Now, here is why it is fast. Because every node holds hundreds of values, the tree stays very shallow. Even for 10 million rows, it is only 3 or 4 levels deep. So the database does 3 or 4 hops instead of 10 million checks. And each hop throws away most of the data that is left. And the tree rebalances itself as you insert new rows, which is how it stays shallow and the table grows. That is the whole magic. But, and this is the part people forget, an index is not free. Two costs. One, it takes extra storage since it is a whole separate structure. And two, and more importantly, it slows down writes because every time you add or change a row, the database has to update the index as well. So the rule is put an index on the columns you frequently search or sort by, like email or order date. But do not index everything, or your writes will become very slow. And you can also make a composite index on two columns together for queries that filter on both. So, in our store, indexing is what makes login by email or find by orders feel instant, even with millions of rows. But even a fast, well indexed database has limits. If millions of people hit it at once, it becomes a bottleneck. So, the next idea is about not asking the database so often, and that is caching. Okay, our database is fast, but it can still only handle so many requests per second. And the same popular product page might be requested a million times an hour. Asking the database to fetch the exact same data a million times is wasteful, and eventually it becomes a bottleneck. So the idea is keep a copy of the answer somewhere much faster and reuse it. And that copy is called a cache. This is one of the most important scaling tools there is. A cache at high level is a small, extremely fast store, usually kept in memory, using something like Redis or Memcached that holds recently used data so you do not have to go all the way to the slower database. Memory is far faster than disk. So a cache hit can be, let's say, 100 times quicker than a database query. And the most common pattern is called cache aside, and it is worth knowing by name. It works like this. A request comes in for the product price. The server first checks the cache. If the data is there, we call that a cache hit. It returns it immediately and never touches the database. If it is not there, a cache miss. The server goes to the database, gets the data, stores a copy in the cache, and returns it. So the first person pays the slow price. Everyone after them gets the fast one. The whole point is to get as many hits as possible. There are other patterns as well. Write through, where you update the cache and database together, and write back, where you write to the cache first and the database later. But cache aside is the one to know first. Now, caching has two famous hard problems and they are worth knowing properly. The first is eviction. A cache is small, so when it fills up, it must throw something out. The most common rule is LRU, least recently used. Throw out whatever has not been touched in the longest time. And each entry can also have a TTL, a time to live, after which it expires automatically. And the second, harder problem is invalidation. The fact that a cache is a copy, so when the real data changes in the database, your cached copy is now wrong. It is stale. Deciding when to update or delete cached copies is genuinely one of the hardest problems in this field. And there are two standard ways to handle it. One, whenever you write a row in the database, you also delete that key from the cache. So the next reader is forced to fetch the fresh value. And two, you simply accept a short TTL, let's say 60 seconds, and live with the data that is almost 60 seconds old. Most real systems use a mix of both. And there is one more called a cache stampede. If a popular cached item expires, suddenly thousands of requests all miss at once and hit the database together, which can overwhelm it. And the fix is quite simple. You let one request go and rebuild the value while the others wait for it. And you spread the expiry time slightly so 1,000 keys do not expire in the very same second. Worth naming. So, in our store, caching is what lets a hugely popular product page be served instantly to millions while barely touching the database. But there is one kind of slowness even a cache cannot fix, the physical distance between the user and the server. And the fix for that is our next concept, the CDN. Okay, so caching made our database faster, but here is a different kind of slowness. Our server might be in, let's say, America and a user in India. Now, no matter how fast our server is, the request has to physically travel across the planet and back. And that distance alone adds real delay because even at the speed of light through cables, it is a long way. And this matters most for the big files, images, videos, style sheets. So, how do we fix distance? We bring the content closer to the user, and that is CDN. CDN stands for Content Delivery Network. At high level, it is a large set of servers spread all over the world. These are called edge servers, and each one keeps a copy of your website's static content, the images, the CSS, the JavaScript, sometimes whole pages. So instead of every user fetching an image all the way from your one server, they fetch it from an edge server near them. Someone in India gets it from an edge in India. And how does your browser even know which edge is nearest? This is where DNS comes back from part 1. When you look up the address for that image, the CDN's own DNS servers look at where the request came from and answers with the address of an edge close to you. So, a user in India and a user in Germany ask for the exact same name and get back two different addresses. You do nothing, the answer itself is personalized. The distance and therefore the delay drops massively. And how does the content get to all those edge servers? The common way is called pull. The first time a user in a region requests an image, the nearby edge does not have it yet. A miss, so it fetches it once from your main server, which we call the origin, keeps a copy and serves it. Every user after that in that region gets the local copy, a hit, just like our cache, but spread across the globe. And it uses a TTL as well to decide how long to keep each copy before checking the origin again. One important distinction, a CDN is mainly for static content, the stuff that is the same for everyone. Images, videos, files, your personalized content, your cart, your account page is dynamic, different per user, so it usually cannot be cached at the edge and still goes to your server. So, in our store, the CDN is what makes product images and pages load quickly for users everywhere in the world, while also taking huge load off the main servers. And that closes part 2. We now have a server, a database, an index, a cache, and a CDN. One of everything running nicely. But what happens when one of everything is not enough? When the traffic is simply too much for a single mission? That whole question, scaling, is part 3. See you there. Welcome back. This is part 3. So far, across the first two parts, we have built a single server with a database, an index, a cache, and a CDN, and it works nicely. But this part asks the big question: what happens when one of everything is not enough? When millions of people arrive at once? This whole part is about scaling, load balancer, statelessness, replication, sharding, and famous cap theorem. Let's begin. Okay, our store is getting popular, thousands of people at once, and our one server is struggling. It simply cannot answer everyone fast enough. So we need to grow, and there are exactly two ways to grow, and knowing the difference well is interview basics. The first way is vertical scaling, also called scaling up. This just means make the one machine bigger, more CPU, more memory, a faster disk. And honestly, it is the simplest fix. You change nothing about your code, you just rent a stronger machine. And it has two hard limits. One, there is a ceiling. You cannot buy an infinitely powerful computer, so eventually you run out of bigger. And two, and this is a serious one, it is still just one machine. So if it fails, your entire site goes down. We call that a single point of failure. One thing whose failure takes everything with it. The second way is horizontal scaling, scaling out. Instead of one bigger machine, you run many ordinary machines, all doing the same job, sharing the load between them. And this is powerful for two reasons. One, there is basically no ceiling. You need more capacity, you add more machines. And two, there is no single point of failure at the app server layer. If one machine dies, the others keep serving, and users do not even notice. The catch is that it is more complex. Now you have many machines and you need something to spread the traffic across them, and they cannot each keep their own private memory of users. And solving those two problems is literally the next two concepts. So in our store, we choose horizontal scaling. Many servers, no ceiling, no single point of failure. But the moment you have many servers, you hit an obvious question. When a request comes in, which server should handle it? And the answer to that is one of the most famous components in all of the system design, the load balancer. Okay, we now have, let's say, 10 identical servers, but the user's browser only knows one address. So something has to sit in front, receive every request, and decide which of the 10 servers should handle it. That something is a load balancer, and it is one of the most important pieces in any large system. At high level, one front door, one public address, hiding a whole group of servers behind it, and spreading the requests evenly across them. Now, how does it decide which server? There are a few standard methods and you should know them by name. The simplest is round robin. Just go in turn. Server 1, server 2, server 3. Go back to 1. Next is least connections. Send the request to whichever server is currently least busy, which is smarter when some requests take longer. And there is IP hash. Use the user's address to always send the same user to the same server. And that has a name, a sticky session, sending a user back to the server that already knows them. It works, but as we'll see in a moment, the cleaner way is to keep servers stateless instead. And finally, you can add weights to send more traffic to your more powerful machines. And here is a critical job of the load balancer, health checks. The load balancer constantly pings each server behind it, asking, are you alive and healthy? And the moment a server stops responding, the load balancer stops sending it traffic. It routes around the dead one automatically. This is exactly what gives us that no single point of failure we wanted from horizontal scaling. So, in practice, you never just run one, you run at least two, and the traffic is pointed at whichever one is healthy. One server dies, the load balancer quietly skips it. User notice nothing. One more distinction for the interview, load balancers come in at two levels. A L4 load balancer works at the transport level. It only looks at IP addresses and ports, so it is very fast, but not very smart. An L7 load balancer works at the application level. It can actually read the request, the path, the headers, so it can do smart routing, like sending slash images to one group of servers and slash checkout to another. L4 is fast, L7 is smart. And quickly, you will hear three related words that confuse people: reverse proxy, load balancer, and API gateway. They are all front door components, and honestly, they overlap. A reverse proxy is the general receptionist in front of your servers. A load balancer specifically spreads load. And an API gateway, which we will meet later, adds smart features like authentication and rate limiting for many services. Same family, different focus. So, in our store, the load balancer is single address that the world talks to, quietly spreading every request across our fleet of servers and skipping any that die. But this creates a subtle new problem. If your requests are landing on different servers each time, how does any one server remember that you are logged in? And that is our next concept, statelessness. Okay, so remember, HTTP is stateless. The server does not automatically remember you. And now it is worse because with a load balancer, your first request goes to server A and your next one might be going to server B, a completely different machine that has never seen you, right? So, if server A stored this user is logged in its own memory, server B has no idea. So, how does the store remember you across requests and across servers? First, the golden rule and a very common interview point. Your servers should be stateless, meaning no server keeps any personal per user memory of its own. Why? Because if any server can be handling any user at any time, none of them can rely on private memory. And the big benefit is that this makes your servers interchangeable. You can add, remove, or restart any of them freely, which is exactly what makes horizontal scaling work. So, the state, your login, your cart must live somewhere shared, not inside one server. So, where does it live? It starts with a cookie. A cookie is just a small piece of data that server gives your browser, and your browser automatically sends it back on every future request. So, the server can put a little identifier in a cookie, and now every request carries that identifier. And there are two main ways to use it. The first way is server side sessions. When you log in, the server creates a session, the record that says this ID belongs to this logged in user, and stores it in a shared place that all servers can reach, like a Redis store. It gives your browser just the session ID in a cookie. Now, on every request, any server reads that ID, looks it up in the shared session, and knows who you are. The benefit, you can instantly cancel a session like a logout. The cost, every request needs that extra lookup. The second way is a JWT, a JSON Web Token. Here, instead of storing a session on the server gives your browser a signed token that already contains your identity, like user42 logged in, with a cryptographic signature that proves the server created it and nobody tampered with it. And how does that signature actually work? Our servers share one secret key that only they know. The server takes the contents of the token, mixes them with that secret, and runs the whole thing through a one way scrambling function. And the result is the signature stuck on the end. So, when any of our servers receives the token back, it does the exact same calculation itself and compares. If even one character of that contents was changed, the result will not match and the token is rejected. So, our servers share one small secret key instead of one big session store. And one important point to get right, the token is readable by anyone who has it. The signature only stops it being forged, it does not hide what is inside. So, you never put secrets in it. So, now any server can just verify the signature and trust the token. No lookup, no shared store needed. The benefit, it scales beautifully. No database hit. The cost, it is harder to cancel early because the token is valid until it expires. Sessions versus tokens, lookup but revocable versus no lookup but hard to revoke. This is the classic trade off between the two. So in our store, statelessness plus a shared session store or a JWT is what lets any of our many servers recognize you, no matter which one you land on. Now, we have scaled our servers out nicely, but all of those servers are still talking to one database, and that is now the bottleneck. So the next few concepts are all about scaling the database itself, starting with replication. Okay, we have many servers now, but they are all reading and writing to a single database, and that is a two problems at once. One, that single database is now a bottleneck and a single point of failure. If it dies, the whole store dies. And two, it can only handle so many reads per second, so we need more than one copy of the database. And the first technique for that is replication. Replication means keeping multiple copies of the database in sync. The standard setup, and know these words, is a leader and follower, sometimes called primary and replica. There is one leader, and it is the only one that accepts writes, creating orders, updating stock. And there are one or more followers, which are copies of the leader, and they handle reads. And how does that copying actually happen? The leader writes every single change it makes into an ordered log. Insert this row, update that one in order, and each follower stays connected to the leader, reads that log as it grows, and applies the exact same changes in the exact same order. So a follower is not guessing, it is replaying the leader's history. And this buys us two things. One, we can now handle far more reads because we can add many read replicas and spread all the read traffic across them, while the leader focuses on writes. Most applications read far more than they write, so this is huge. And 2, if the leader dies, we can promote one of the followers to be the new leader. This is called a failover. So the database is no longer a single point of failure. And that promotion is not a person doing it in the middle of the night. The machines watch each other, and when enough of them agree the leader is gone, they vote on which follower takes over. And the reason they vote instead of any one mission deciding is to avoid ending up with two leaders accepting rights at once, which is a genuinely bad situation. But there is one catch that matters a lot in practice, so understand it well. How the copying happens matters. In asynchronous replication, the leader confirms your rights immediately and copies to the followers a moment later. This is fast, but it means the followers can be slightly behind. We call this replication lag, and it causes a classic bug. You update your profile photo, the write goes to the leader, but your very next read happens to hit a follower that has not caught up yet. So you see your old photo. This is called the read your own writes problem. The alternate, synchronous replication. Wait for the followers before confirming. So no lag, but slower writes. Fast but stale or slow but fresh. That trade off is the whole thing. And one more real risk with asynchronous replication, if the leader dies before it has copied its last few writes to the followers, those writes, which it already confirmed to the user, can simply be lost in the failover. So, failover is not entirely free either. So, in our store, replication lets us handle a huge amount of read traffic and survive a database failure. And one thing people get caught by, replication is not a backup. Replication protects you if a machine fails, but it faithfully copies your data mistakes as well. If you accidentally delete data, every replica deletes it too. So, you need real backups taken regularly that let you restore to any earlier point in time. Now, but replication makes copies. Every copy still holds the whole dataset. So what happens when the data is simply too big or the writes are too many for any single machine to hold? For that, we split the data itself, and that is sharding. Okay, replication copied the whole database, but sometimes the data is just too large to fit on one machine at all. Or there are too many writes for one leader to handle. So instead of copying the whole thing, we split it. Each machine holds only a part of the data. This is called sharding, also known as partitioning, and it is a favorite interview topic. The idea, you take your data and divide it across multiple databases called shards, where each shard holds a different subset of the rows. For example, users with names starting A to H on shard 1, I to P on shard 2, and so on. And the crucial decision is the shard key, the piece of the data you use to decide which shard a row goes to, like the user ID. A good shard key spreads the data evenly. A bad one piles everyone onto one shard. There are two main ways to split: range based, like the A to H example, by ranges, and hash based. You run the key through a hash function to get a number, and that number decides the shard. And since we will use this word a few more times, a hash function at high level is just a function that takes any input, let's say a user ID, and turns it into a fixed number. And two properties makes it useful here. One, the same input always gives you the same number, so you can always find that row again later. And two, the numbers come out spread evenly, so your rows land across all the shards roughly equally instead of piling onto one. Now, here is the hard part, and it is the bit worth actually understanding. The naive hash approach is take the ID, do ID mod the number of shards. That works fine until you add a new shard, because now the number of shards changed, so almost every key maps to a different shard than before, and you had to physically move nearly all your data. That is a disaster, and the classic fix is called consistent hashing. The idea at high level, you arrange the shards in a circle or ring, and each key falls at a point on that ring and belongs to the next shard clockwise. And how does a key fall at a point? You hash it, and that number is its position on the circle. And you hash each shard's name as well. So the shards sit at their own points on the same circle. Now, here is the beauty. When you add a new shard, it lands at one point and it takes over only the keys sitting just before it. Every other key looks clockwise, sees the same shard it saw yesterday, and it does not move at all. This is a whole difference from the modern approach where changing the number changes the answer for every key. That is why consistent hashing is such a famous important idea. And there is a common refinement worth naming: virtual nodes, where each real shard is placed at many points around the ring instead of one, which spreads the load more evenly and smooths things out when a shard joins or leaves. And one problem to name: hot shards. If one particular value is extremely popular, say one celebrity user, The shard holding them gets far more traffic than the others. So a good shard key also avoids these hotspots. So in our store, sharding lets us grow past the size of any single machine, and consistent hashing lets us add capacity without moving all our data. Now, once your data is spread and copied across many machines, a deep question appears. Can all these copies always agree and stay available at the same time? That question has a famous answer, and that is our next topic, the cap theorem. Okay, so now our data lays on many machines, copied and split, and this raises one of the most famous ideas in all of system design, the cap theorem. It is three letters. C is consistency, every read sees the latest data, everyone agrees. A is availability, every request gets a response, the system is always up. And P is partition tolerance, the system keeps working even if the network breaks between the machines. Now, you will often hear the theorem stated as pick two of three, and honestly, that framing is a little misleading, and interviewers like when you know why. You do not really get to give a partition tolerance because the network will break sometimes, whether you like it or not. So, the real situation is this: in a distributed system, when a network partition happens, meaning the machines temporarily cannot talk to each other, you are forced to choose between just two of them, consistency or availability. And since network failures are unavoidable, the network will break sometimes. Partition tolerance is not really optional. So, the real choice in that moment is between C and A, consistency or availability. Let's make that concrete because that is the part that actually matters. Imagine the network splits and a request comes in. You have two options. Option 1, you refuse to answer unless you are sure you have the latest data. That keeps you consistent, but you just become unavailable for that request. That is what a bank does. It would rather show you an error than a wrong balance. Option 2, you answer anyway with the whatever data you have, which might be slightly old. That keeps you available, but you just gave up perfect consistency. That is what a social media feed does. Showing a like count that is a few seconds old is completely fine, as long as it always loads. And this connects to two words you will use constantly. Strong consistency means the moment you write something, everyone sees the new value immediately. Safe but slower and harder to keep available. Eventual consistency means the copies will all agree eventually. But for a brief moment, some might be stale, much easier to scale and keep available. So, money and orders want strong consistency. Likes, views, and feeds are happy with eventual. Picking the right one per feature is exactly the kind of thinking interviews look for. And there is a small extension called PACELC worth naming. Even when there is no partition, you still trade off latency versus consistency. So, in our store, we use strong consistency for orders and payments, and we happily accept eventual consistency for things like product view counts. And that closes part 3. We have now scaled the core system across many machines, many servers, many database copies, split many ways. In the final part, part 4, we cover everything that turns into one real production system: message queues, microservices, the reliability patterns, deployment, and security. See you in the last one. Welcome back. This is part 4, the final one. We have built and scaled the core system. Now we cover everything that turns it into a real production system: message queues, microservices, the patterns that keep it reliable, how it is shipped with containers and Kubernetes, and how we watch it and keep it secure. Let's finish this. Okay, when you place an order, several things need to happen. Save the order, charge the card, send a confirmation email, update the analytics, tell the warehouse. Now, some of that, like sending the email, is slow. And importantly, you, the user, do not need to wait for it. The email arriving 2 seconds later is completely fine. So, making the user wait for all of it would be silly. And the tool that fixes this is a message queue. A message queue at high level is a waiting line for tasks sitting between your services. Instead of doing the slow work right away, a service drops a little message, send this email into a queue, and immediately moves on and responds to the user. And separately, other programs called workers or consumers pull messages off that queue and actually do the work a little later. So the person who produces the work does not wait for it to be done. And this gives you three big benefits, all worth knowing by name. 1. Asynchronous processing. The user gets a fast response, and the slow work happens in the background. 2. Decoupling. The service adding to the queue and the worker reading from it do not need to know about each other or even be running at the same time. They only share the queue. And 3. Load leveling. If a sudden burst of orders come in, The queue simply hands them, and the workers work through them at a steady pace instead of everything collapsing at once. Now, a related idea. A plain queue usually has one message going to one worker, but sometimes you want one event to reach many different services. For example, order placed needs to reach the email service, the analytics service, and the warehouse service. That pattern is called publish subscribe or pub/sub. One event is published and many subscribers each receive it. And the famous tool here is Kafka. Kafka, at high level, is a durable log of events. Events get appended to named streams called topics, and many different consumers can each read through the log independently at their own pace. And here is the key difference from a plain queue. Reading a message does not remove it. The log just keeps growing, and each consumer simply remembers its own position in it. So, the email service can be at a position 900 while the analytics service is still at 500, reading the very same events without either affecting the other. Old events are dropped later by age, not by being read. That is why it is used for event streaming and data pipelines everywhere. And one important detail to get right, delivery guarantees. There are really three levels here, and you should know all three. At most once, a message is delivered 0 or 1 times, so it might get lost but never duplicated. At least once, it is never lost but might arrive twice, and this is the most common one. And where does the duplicate actually come from? At high level, the queue does not delete a message when a worker picks it up. It keeps it hidden from the other workers and waits for that worker to send back an acknowledgement, meaning done. And if that acknowledgement does not arrive in time, the worker crashed or the network dropped it. The queue assumes the work never happened and hands the message to another worker. So nothing is ever lost, but work that actually finished and simply failed to acknowledge gets done a second time. And at most once is just the opposite order. Acknowledge first, then do the work. So a crash loses it instead. And exactly once, delivered precisely one time, which is the ideal but genuinely hard. So in practice, it is usually faked by using at least once plus idempotency, so that a duplicate does not harm. So, because most systems are at least once, your workers must be able to handle the same message twice without doing damage. For example, not sending two emails or not charging twice. That safety property is called idempotency, and we will come back to it shortly. And if a message keeps failing, it gets moved aside into a special dead letter queue, so it does not block everything else. So, in our store, message queues let checkout feel instant, while the emails, receipts, analytics happen quietly in the background. Now, so far, our whole store has been one big program, but at a certain size, teams break that one program into many smaller ones. And why they do that and what it costs is the thing people get wrong more than almost anything else. Microservices. Okay, so far our entire store is one big program. All the code, orders, payments, products in one place. We call that a monolith. And honestly, a monolith is great when you are small. Everything is simple, in one place, easy to run. But as the company grows to hundreds of engineers, that one program becomes a problem. So many teams are all editing the same code, getting in each other's way, and every tiny change means redeploying the whole thing. So the fix is microservices. You break one big program into many small independent services, each owning one area of the business. An order service, a payment service, an inventory service, each with its own code, its own team, and often its own database. Now, the most important point here, and the one people genuinely get wrong, the main reason to do this is not performance. And this one really does matter in a few interviews. Saying, I would use microservices because they scale better is one of the quickest ways to sound junior because it is not why companies actually split. It is about people and teams. With microservices, each small team owns its service and can build, test, and deploy it independently without coordinating with everyone else. That is the real win. Independent teams, independent deployments. And there is a second benefit, fault isolation. Because the services are separate, if the search service crashes, the checkout service keeps working. The failure is contained. But, and you must say this in an interview or you will sound naive, microservices are not free and not always the right choice. Splitting into many services means they now talk over the network, which is slower and can fail. Keeping data consistent across services is genuinely hard because you lose those easy single database transactions. And the patterns to handle that, which are worth being able to name, are things like the saga pattern or two phase commit. And briefly, The saga pattern means you do the steps one after another, each in its own service, and if a later step fails, you run a compensating step to undo the earlier ones. So, refund the payment instead of rolling back a transaction. Two-phase commit is a slitter one. A coordinator first asks every single service, "Are you ready?" And only if all of them say yes, does it tell them commit. It is more correct, but it is slow. And if the coordinator dies, everyone is left waiting. And you now have hundreds of things to deploy, monitor, and debug. So the honest, senior advice is start with a monolith, keep it simple, and only split into microservices when the pain of one big codebase actually forces you to. And two supporting pieces you will hear about. First, with hundreds of services, the client should not talk to each one directly. So you put an API gateway in front, a single entry point that receives all requests and routes them to the right service, and also handles shared jobs like authentication and rate limiting in one place. And second, service discovery. Since services start, stop, and move around constantly, they need a way to find each other's current address automatically. And that is what a service registry does. And the way it works is two simple steps. When a service starts up, it registers itself. I am the payments service and this address. And anything that needs payments asks the registry for the current list and gets fresh addresses back. The registry also health checks them. So anything that has died drops off the list automatically. So, in our store, at large scale, we split into services like orders, payments, and inventory behind an API gateway. So, different teams can move independently. But the moment you have many services talking over an unreliable network, failures become normal. So, the next concept is all the techniques we use to survive those failures gracefully. Okay, in a big distributed system with many services over an unreliable network, failures are normal, not rare. So, a big part of system design is a set of patterns to survive those failures gracefully. Let's go through the four worth knowing. A note on this: the specific algorithms like the token bucket are really prepped for a design a rate limiter question. In a general design interview, it is enough to say that you would rate limit and why. The first is rate limiting. This protects your system from too many requests, whether from one aggressive user or a bad script or an attack. A rate limiter simply caps how many requests someone can make in a given time, say 100 per minute. And once they cross it, it rejects the extra ones with a status code 4 to 9 too many requests. And the main mechanism to know is the token bucket. Picture a bucket that is refilled with the tokens at a steady rate, let's say 100 per minute. Every request takes one token out, and if the bucket is empty, the request is rejected. And because unused tokens collect in the bucket up to its size, a quiet user can suddenly make a small burst of request, which is usually exactly what you want. The leaky bucket is a close cousin that smooths the rate out instead. So, rate limiting keeps any one source from overwhelming you. The second is idempotency, and this comes straight from our queue discussion. Remember, a message or a request can arrive twice. The network is unreliable, so clients retry. Now, imagine that request was charge the card. If you process it twice, the customer is charged twice. A disaster. Idempotency means an operation can be safely repeated with no extra effect. The standard trick is an idempotency key. The client attaches a unique ID to the request, and the server remembers, I already processed this ID, so a repeat just returns the first result instead of charging again. So, a safe retry never double charges. The third is retries with backoff. When a call to another service fails, often the right move is to just try again. It might have been a brief blip, but if you retry immediately and forever, you can make things worse. Thousands of clients flooding a struggling service. So, you use exponential backoff. Wait a little, then double the wait each time, and add jitter, a little randomness, so that all your clients do not retry at the exact same moment and stampede together. Retry, but politely. And the fourth is the circuit breaker, a really elegant one. Imagine one service your stores depends on becomes very slow or starts failing. If you keep calling it, your request pile up waiting and your service goes down as well. The failure spreads. A circuit breaker prevents that. It works exactly like an electrical fuse with three states. Normally it is closed, calls flow through. But if it sees too many failures, it trips to open. And now it stops calling that service entirely and fails fast, giving the sick service room to recover. And after a while, it goes half open. It lets a few test calls through, and if they succeed, it closes again. Closed, open, half open. And the two numbers that make it a real machine. Too many failures is a rule you set. Something like if more than half of the last 20 calls failed, trip. It is always measured over a recent window, not a lifetime total. So old failures do not count forever. And after a while is just a timer. Let's say 30 seconds before it lets those test calls through. This one stops a single failing service from taking down the whole system. So, in our store, rate limiting, idempotency, retries with backoff, and circuit breakers is what keeping the whole thing standing even when individual parts misbehave. Okay, we have now designed the entire system. The last big area is how you actually run in real world, how you package it, ship it, and watch it. And that starts with containers. Okay, we have many services, each needing to run on many machines. And a classic, painful problem shows up. The code runs fine on the developer's laptop, but breaks on the server because the server has a different setup, a different version of something. The famous line, but it works on my machine. So we need a way to package a service with everything it needs so it runs identically everywhere. And that is a container. A container, and the popular tool is Docker, is a lightweight standard box that holds your service plus every dependency it needs, the right versions of everything. And because the box carries its whole environment, it runs exactly the same on a laptop, in testing, and in production. And one honest note before we go on, containers and Kubernetes are not really system design interview material. They belong to DevOps interviews. And in a design interview, leading with I would use Kubernetes actually counts against you. But you genuinely cannot understand how a real system runs without them. So let's do them properly. And the first thing to get right, a container is not a virtual machine. A virtual machine runs a whole separating operating system which is heavy and slow to start. A container shares the host machine's operating system, so it is far lighter and starts in seconds. And what does isolated actually mean here if they are all sharing one operating system? The operating system gives each container its own private view, its own file system, its own list of running processes, its own network address, so it cannot see or touch anything else on that machine. And it also puts a limit on how much CPU and memory that one container may use. So a busy container cannot starve the others. So the box carries the libraries and files your app needs. It does not carry an operating system of its own. It borrows the hosts, and the host keeps everything in their own lane. Now, one container is easy, but a big store runs thousands of containers across hundreds of machines, starting them, restarting the ones that crash, adding more when traffic rises, spreading them across machines. Doing all that by hand is impossible. So you need a system that manages them for you, and that system is Kubernetes. Kubernetes, often written K8s, is an orchestrator. It runs and manages your containers across a whole fleet of machines, and its core idea is genuinely elegant and worth stating clearly. You declare the desired state. For example, I always want 5 copies of the order service running, and Kubernetes constantly works to make reality match that. It is exactly like a thermostat. You set the temperature you want, and it does whatever it takes to reach it. So, if one of your 5 containers crashes in the middle of the night, Kubernetes notices and starts a new one immediately. So this is called self-healing. It if traffic spikes, it can start more copies, auto-scaling, and it can roll out new versions gradually. And one more honest note, most small projects do not need Kubernetes. It is powerful but complex, and it is only worth it once you truly have many services at scale. Reaching far too early is a very common mistake. So, in our store, containers package each service to run identically everywhere, and Kubernetes runs and heals thousands of them without a human watching. Now, we can package and run our services, but how do we ship a new version of the code safely without taking the site down? That is our next step, CI/CD. Okay, so our code is written, packaged in containers. Now, how does a new version actually get onto the live servers safely and ideally many times a day? Doing this by hand is slow and dangerous. So, teams automate the whole thing, and that automation is called CI/CD. Let's split the two letters. CI is continuous integration. Every time a developer makes a change, it is automatically built and tested right away. So, bugs get caught within minutes, not weeks, and the code is always in a working state. And CD is continuous delivery or deployment. That same tested changes then flows automatically out to the servers. Together, they form a pipeline. Code, then build, then run the tests, then deploy automatically every time. Now and again, CI/CD is DevOps territory rather than a system design interview topic, but it is how every real system actually ships, so it is worth knowing. The interesting part is how you deploy a new version without downtime. There are three standard strategies. The first is a rolling deployment. You replace your servers with a new version, a few at a time, so the site stays up throughout. A second is blue green. You keep two complete environments, blue running the current version and green running the new one. You test green fully, then switch all traffic over in one stint. And if something is wrong, you switch straight back. And the third, the safest, is a canary deployment. You release the new version to just a small percentage of the users first, say 5%. Watch closely for errors, and only if it looks healthy do you roll out it for everyone. And the single most important safety net, rollback. If a new version turns out to be bad, you must be able to instantly go back to the previous, known good version. A good deployment system makes rollback fast and reliable, which is exactly what you want when something breaks in the middle of the night. So, in our store, CACD lets us ship improvements many times a day, safely using strategies like canary releases and rollback in seconds if something goes wrong. Now, our system is built, running and updating itself. But with hundreds of services, one final question remains. When something does go wrong, how do you even see it? That is observability. Okay, our store is now hundreds of services across thousands of containers. And one day a user says checkout is slow. Now, where do you even look? You cannot open each of a hundred services and read its memory. So you need to build the system so it can explain itself. And that ability is called observability. And it stands on three pillars. And a useful note here, in interviews, observability usually shows up as a design prompt, as in design a monitoring system rather than as theory you get quizzed on. What does get noticed is simply that you think about how the system is watched instead of ignoring it. The first pillar is metrics. Metrics are just numbers over time. Request per second, error rate, average response time, CPU usage. They answer the question, is something wrong? You put them on dashboards and you set alerts. So if the error rate suddenly spikes, the system automatically pages an engineer. There is a well known set to remember called the golden signals. Latency, meaning the delay before a request completes, plus traffic, meaning how much demand is arriving, request per second, errors, meaning what share of those requests failed, and saturation, meaning how full your system is, how close the CPU, the memory, or the queue is it to its limit. And saturation is the interesting one because it warns you before things break, while the other three tell you it is already breaking. Metrics are your early warning that something is wrong. And closely tied to metrics is a framing worth knowing. Availability targets. The SLO and error budget vocabulary below is really SRE territory, not system design. But how many nines does come up when you state your requirements? You will hear a system described as 3 nines or 4 nines. That just means 99.9% or 99.99% uptime. And the teams set an SLO, a service level objective. A target like 99.9% of requests should succeed, while an SLA is an actual promise to the customer, often with a refund if you miss it. And there is a clever idea on top called error budget. If your target is 99.9%, then that remaining 0.1% of failures is your budget to spend. As long as you stay within it, the team is free to ship fast. So, nines, SLO, SLA, and error budget, those four come up again and again. The second pillar is logs. A log is a detailed timestamped record of individual events. User 42 tried to check out. Payment failed with this error. Log answers the question why did it break? The detailed story. And the key practice, logs should be structured and tagged with a request ID. So you can filter all the log lines for one specific request across the system. Unstructured just means the log line is written as named fields, user ID, order ID, status, duration, instead of one English sentence because a machine cannot reliably search sentences, but it can search fields instantly. And all those lines are shipped off the individual machines into one central system, which is what lets you search across hundreds of services in one place. And one rule you should state out loud, never log secrets, no passwords, no card numbers. And the third pillar, the one people completely forget, is tracing. Remember in microservices system, a single request might hop through a dozen different services. A trace follows one request across all of those services, showing how long it spent in each. So it answers the question, where in this whole chain did it get slow? It works by attaching a unique trace ID to the request, which is passed along to every service it touches. So you can stitch the whole journey back together. And how does that stitching happen? The trace ID writes along in a header on every internal call. So all 12 services see the same ID and each service separately reports its own little record. I had traced ID X. I started here, I finished here, and that piece is called a span. A collector then groups every span carrying the same ID, lines them up in order, and you see the full journey with the slow one standing out immediately. Metrics say if, log says why, traces say where. So, in our store, observability through metrics, logs, and traces is what lets us actually run this huge system and find and fix problems quickly. Now, there is one area we have touched on but not faced directly, and it runs through everything, keeping the store and its users safe. So, let's finish the building with security. Okay, our store handles passwords, personal details, and money, so security cannot be an afterthought. And the first thing to get crystal clear, because interviews test the confusion here, there are two different ideas: authentication and authorization. Authentication is who are you, proving your identity, like logging in. Authorization is what are you allowed to do, checking permissions like can this user view someone else's order. Logging in does not mean you are allowed to do everything. Auth N is identity, Auth Z is permission. Now, authentication starts with passwords, and there is a hard rule you must know. You never store passwords as plain text. Never. If your database leaks, every password is exposed. Instead, you store a hash of the password, a scrambled one way version that cannot be reversed back into the original. And one important detail, you use a deliberately slow hashing function built for passwords like bcrypt or argon2, and not a fast one like SHA-256, precisely so that an attacker trying to guess millions of passwords finds it far too slow to be worth it. And you add a random salt to each one, a bit of random data mixed in, so that two people with the same password still get different stored values. And the salt is not a secret, it is stored right next to the hash in plain. And that is fine. And it is also how login works. You take the stored salt, mix it with the password they just typed, hash it, and compare. The real point of the salt is that an attacker cannot guess one password, hash it once, and match it against a million stolen accounts with a different salt on each. He has to attack every account separately. When someone logs in, you hash their attempt and compare the hashes. And after login, you give them a session or a JWT, exactly as we discussed earlier. And you will hear OAuth. At high level, it is a standard that lets one app get permission to act on your behalf in another app without handing over your password. So, what actually happens when you click login with Google? Our store sends you over to Google. You log in there on Google's own page, and Google asks you, do you allow this store to see your name and email? If you say yes, Google sends your browser back to us with a short one time code. Our server then calls Google directly, hands over the code plus its own secret, and gets back an access token, basically a string that stands for that permission. And after that, our server calls Google's API with the token. So your password only ever goes to Google, and our store only ever holds a token which can be cancelled at any time. And login with Google is built on top of it using an extension called OpenID Connect. So, a small, precise point worth getting right. OAuth itself is really about authorization, permission, and the actual login, the identity part, is OpenID Connect, sitting on top of it. Either way, your store never even sees your Google password, worth knowing by name. And encryption, quickly in two places. In transit, data moving over the network is protected by TLS, the HTTPS we set up at the very start. And at rest, data sitting in your database and storage should be encrypted as well. So, a stolen disk is useless. Encrypt both. And finally, three classic attacks worth being able to name with one line defenses. To be straight with you, this level of security detail belongs to a security interview, not a system design one. In a design interview, it is usually a single line about which endpoints need authentication. But you should still know these as an engineer. SQL injection. An attacker sneaks malicious commands into input field to trick your database. The fix is to never build queries by pasting user input, but to use parameterized queries. XSS, cross-site scripting. An attacker injects malicious scripts that run in other users' browsers. The fix is to carefully escape any user content before showing it. And CSRF, cross site request forgery. A malicious site tricks a logged in user's browser into making a request they did not intend. The fix is a secret token that only your real site knows. Name the attack, name the fix. So, in our store, security means proving identity, checking permissions on every action, hashing passwords, encrypting everything, and defending against the common attacks. And with that, we have actually built the entire system end to end. So, let's step back and see the whole thing together. Okay, let's put the whole picture together because this is what an interview really is testing. Not just the pieces, but how they fit. You open the store, DNS turns the address into server's IP. Your browser opens a reliable connection with TCP, secured by TLS, that is HTTPS. It sends an HTTP request. The big static files come from a CDN near you. The request hits a load balancer, which spreads it across many stateless servers. A server checks a cache first and only asks the database which is replicated for reads and sharded for size if it has to. Slow work like emails is dropped onto a queue for workers to handle later. At scale, the whole thing is split into microservices, protected by rate limiting, retries, and circuit breakers, all packaged in containers, run by Kubernetes, shipped by CI/CD, watched by observability, and wrapped in security. And that is a modern website, end to end. Every single piece exists to solve one specific real problem. Being found, being fast, handling scale, surviving failure, staying correct, staying safe. And you now understand not just what each one is, but why it exists and how it connects to the rest. And honestly, this is exactly what a system design interview is checking. And it also the difference between using these tools and actually understanding them. And that part stays with you long after any one interview. And that is the whole series. Four parts, one complete picture. From a single request all the way to a running scaled production system. So go back through the concepts that felt shaky, say them out loud in your own words, and you will be well prepared. If this helped you, subscribe, and the full playlist is right there to revisit any part before your interview. Thank you for watching all four parts, and good luck.